Let's see. It works. Yeah. Yes. Okay. Okay. Please tell me is you can hear like. So I have to start again. Anyway, so I was saying I will spend it's like 4 parts. The first part I will talk about Clifford algebras. The second part about a little bit of operator theory. Then the most juicy part will be the radiation conditions. That will be like the technical part and then some applications. So for me, the language is going to be slightly different that for many of you. By Clifford algebra, I will denote it by CLM. It's going to be the enlargement of CM such that I will use a dot, this product for the Clifford algebra. So x times Clifford algebra product x will be minus the norm of x. And so it's not signature or signature M. So we had only two. If we had the standard orthonormal basis, the Clifford algebra is generated with these two relations. E to the square is equal to -1 and they anti-commute. And yes? Like this? Okay. No, it's the point, this fell down. Is I do it like, okay, let's see. I do it as many times as needed, but okay. So with these two relations, we generate the Clifford algebra, making all the products. So it will be the so any element will be the increasing, strictly increasing of these basic elements in increasing order. I mean, with the multiplicative unit. And I will take it as a natural Hilbert structure. So the dot product will be denoted by this. And we had a few, like the Clifford conjugation will be this and extended linearly. And also the complex conjugation will be just to take this, the conjugate on each component. And I want to split it, so to take it for any L in 0 and M, we are going to take the elements of order L, and we call the range by lambda LM. So it will be the homogeneous part of degree L, and this will split our Clifford algebra as follows. So these are the scalars, just
elements on complex, just the complex numbers. These are the 0-degree elements. So the 1-degree elements are going to be vectors. This is just a copy of CM. Then the bivectors and so on. And this will be interesting. Well, these are like differential forms, these degrees. We're going to take functions defined with values on the Clifford algebra. So for us, a scalar will be something that is here. A vector field will be something that his values are just here, and so on. And that will give us some freedom to do certain things. Anyways, when we take a vector and we take a U homogeneous of degree J, and we do the Clifford product, because of these two relations, the degree will either increase 1 or decrease 1. And I'm going to call the exterior product the part that goes up, and the interior product the part that's go down. So this is like saying that the Clifford algebra is really the exterior algebra plus the inner product. That's the original definition of Clifford. So the Grassmann algebra plus the inner product. And these are here. And so what we have is this relation, the Clifford product, like the inner and the exterior product and the inner product. And we extended linearly for any U with this splitting that I was saying before. So this Clifford algebra formalism is going to say, well, we take an element in the complex, it's just multiplication, and this is 0. 2 vectors will be the inner product, and this is the exterior product of that we have. This is. And a little bit of algebra, slight lemma, just to show you the algebraic formalism. If we do this twice, it's going to be 0, just because of degrees. Also, the adjoint of the inner product will be the exterior product, and so on. And the next property is when we do a little bit of geometry. And I'm going to say exactly what is this. Is we take two vectors. First, we do the exterior product, the interior product. I'm sorry, I am not. The interior, then the exterior with B and A, and the same thing, but first now with the exterior, first A, and now B, and we have this is equal to the inner product with U. This is just linear algebra, but it's gonna be important. And so what this really allows is that we take a vector U of norm 1, we can decompose this as the normal part for any element on the Clifford algebra, as the tangential part and the normal part. And we also had a Pythagoras theorem like this one. And I want to show you this picture that I want to put it. It's very elementary because the first time I learned about the quaternions was from Adolfo, and he showed me a picture like this one. Then he put this back and the orthogonal groups and so on. And well, this is exactly what we had here. The orthogonal and the tangentials. I may say it backwards. Anyways. So this is the Clifford algebra formalism that I was telling you about. And a bit of Clifford analysis, it's just the Dirac operator will be to take this, the partial, take the Clifford product with the base and to sum And we are going to take functions defined on some domain in Rn, C1, and with values on the Clifford algebra. And the standard in this system is to call it monogenic, which is, for us, more important will be the perturbed Dirac operator is to take a k. And here, by the way, I forgot to say, there is an n and an m. And we are going to be working on the bigger algebra. Sorry. And for the perturbed operator will be to take k and to take an extra unit and to make the Dirac plus this time. And these two are important because the Dirac to the square is minus the Laplacian and dk to the square is minus the Helmholtz operator. So any function which is monogenic will have harmonic components, and any function which is k monogenic will have Helmholtz components. And also we can do with this the Hodge-de-Ram formats list like this. We are going to define the exterior derivative, and the interior derivative is just to take the EJs with the exterior product and the EJs with the interior product with the negative sign. And from this, it follows that then the Dirac operator will be the sum of these two. That like the exterior product is just for scalar value, is just the gradient of the function. And so we automatically get that d to the square and delta to the square is 0. And we have this factorization of the Laplacian. And so the time for time harmonic Maxwell system will be two functions with C infinity with values in the Clifford algebra which satisfy this system. So the interior derivative of E equal to EK and the exterior derivative of H equal to EK minus EK E. And very important is that if they satisfy the Maxwell system, then of course the E is 0 and delta H is 0, and E and H are solutions to the Maxwell, to the Helmholtz operator. Okay. This is a bit technical, but just to telling you that this is like a integration by parts or derivation. The way these operators act with this multiplication for the exterior product and the interesting part of this, I'm not going to go over all the details here, but the point to make is here. If we had a null solution of the Helmholtz operator, then this function will satisfy also the Helmholtz operator. And what is this function? This is the harmonic oscillator. So this is something that for us should be in the books, in any elementary books, that something satisfies Helmholtz. Then this, the harmonic oscillator, is also Helmholtz. And things will get a bit more complicated than that, but these two. And so it's more like a language. So that I'm just showing you the language. Okay, so these are, now let me go to really business. The radiation conditions. So we will work on an exterior domain. So this is really in scattering theory. Like what we want to do in the sense, this is to do, it's like going all the way with the scattering theory in m dimensions with values in Clifford algebras. And I'm going to show you just the first step. So we take an exterior domain, that's the complement of a compact set in Rn. We take a wave number. So we take usually the Helmholtz operator, it's a wave. This is a modulus weight. And for us, the fundamental solution of the Helmholtz operator, I remind you, it's a phi k. It's given in terms of a Hankel function of this order, normalized with some values. Okay, I know I can see some faces, but this is a function. Yeah, I am not going to be that technical with these kind of things. But so the non-radiation condition, as I said, we are going to study some set of functions, and the delicate part came here. That's in the radiation conditions. So in 1912, Sommerfeld introduced this condition for a function to solve a boundary value problem, to get uniqueness. And the condition was in terms of the function u and in terms of his derivative. Turns out to be they have to decay in this order as x goes to infinity. And it's a nice condition, has to do with, has some analysis and some algebra in it. So that's what we find. So he came with this condition, and he proved that then you had a uniqueness for a Dirichlet problem in the exterior domain. And was very useful for scalar functions. But on the other hand, in 3 dimensions for the Maxwell system, which I take the usual standard Maxwell system in R3, is this. The radiation condition for these kind of functions were given by Müller and Silver, and these are these two. And we start seeing that from this and this, they look very different. So part of our job was to understand why they look so different. I mean, as I said, a solution of Maxwell is also a solution of Helmholtz, but the solution, the conditions are completely different. And so the part of the things that kind of more than summary is that kind of the reason, I'm not going to say the reason completely, but is that in this context we had several factorization of the Laplace operator. So this is the standard one. We had also with the Dirac operator, and we had with this delta. So for each one factorization, we had one condition, and so that's why they look so different. So we had many conditions, and so I'm gonna go for one theorem. Let me see. I had many things. Okay, I am fine. So we take an exterior domain. This is the first main theorem. And we fix some cake, and we had a solution of the Helmholtz operator. And the following radiation conditions will be equivalent. One with the Dirac operator, and with the function that decays of this order. And once we had the radiation conditions are more given in this sense, this is point-wise, but it's really a whole of set functions. We can give it with the small o, we can give it with in L2, we can give it in several versions in L2, and we can give it with big O, with a different degree. So what really means is that the class of functions kind of self-improves in this with these conditions, and really it's a Cauchy-Schwarz inequality that we prove it in the other way. It is really what it really means. So this is one condition with the Dirac operator. We had another with the delta and with the exterior derivative and with the interior derivative and with these products. And this condition will generalize Silver-Müller. Also, we can even say things about the scalar cases. In the scalar case, this condition is new, that we can decompose the Sommerfeld radiation condition as these n conditions. And I use a small O here and big O, and all can change with the small and big. We actually got a huge number of equivalents. And this is the standard Sommerfeld radiation conditions. And why are these important? That's what I want to give you a little bit of a taste why these radiation conditions are important. Well, in part, they are important because having a radiation condition will be equivalent to having an integral representation formula. And here we had one. Also we can work with the boundary of the domain could be, here I put exterior alpha regular, just very bad, could be very bad. I'm not gonna enter in the details. And so B will denote the unit, the outward unit normal. And so we had radiation conditions if and only if we get integral representations. So like this one, we have the product of the function in the boundary, the normal, and the fundamental solution of the decay of that one, and plus another terms. So this is very similar to Cauchy's integral representation formula. And we had other two. In the case of with the delta and exterior, we have it completely different. This in the literature in R3 is called the Staton-Chu formula, and engineers use it in 3 dimensions. And we had the standard, the green formula with the normal derivative, and this is the also. So each one of these are equivalent, but they are different. The 3 of them are different. So there are like the degree that we had can do things. Okay. So let me do a few applications of these representation formulas. So we are going to say that the function that satisfies Helmholtz will be radiating. Is it satisfy any of the conditions? For these kind of functions, we are going to get some asymptotic behavior at infinity, which is like as follows. We are going to have, we can split our function in the radial part, that's going to be this part, really easy, and some angular part. So the angular part will be a function defined on the sphere with values on the Clifford algebra that is called the far-field pattern, and is really used in many applications in R3 or R2. And that has like this. And the nicest thing about this is that the far-field mapping, that is to associate each radiating function is far-field, is a one-to-one function. And that's used a lot for scattering theory. And I put just a few, it's a C-infinite function on the sphere. Yeah, well. Also, the far-field pattern encodes information, and we can do some calculus similar. And we had integral representation formulas actually for each. I didn't want to put you many details, but for each integral representation formula, we had a formula for the fat field pattern. And so, as I was saying, the fat field pattern gives us, it's like the DNA of the function. And one application, so if we consider a differential operator with now the alpha and Clifford product, either exterior or interior, and we take this radiating function and we take then the function u applied to this differential operator is also radiating, that's clear. But what's important is that the far field pattern is just given like this. It's just, we had similar to Fourier transform. We had the calculus similar to the Fourier transform. And as a corollary, we get that the far field pattern for du is just multiplication by w, and by delta is multiplication by ek minus ek w with the interior product. So in particular, we are going to be able to read whether Maxwell or K monogenic from the far field pattern. And this is this corollary. Suppose that we had two radiating functions, then E and H solve the Maxwell system if and only if the far field patterns are related by these two relations. So what are we saying? Well, and we let me explain this with the K monogenic. We can also say we got a radiating function, and we're going to say that it's radiating if and only if his far field pattern is a divisor of 0 of this form. And this is interesting also because U is a satisfied second order system. And here we are saying that we satisfy a first order system just from knowing his value at infinity. That's the nice part. And okay, we can also say the following. This is just an extra unit in the Clifford algebra. We start with the n or m units in our m plus 1. So we got a radiating function, and we take the harmonic oscillator of the function. As I said before, this turns out to be Helmholtz. But to be radiating turns out to be really technical. This is a technical part, but we prove it. And also, we prove something really nice, I think, that we didn't expect it, that his far field pattern turns out to be of the radiating oscillator of U, turns out to be to take the far field pattern of U and take the extension of this in the harmonic oscillator of U, which is well defined, and that turns out to be the far field pattern. And this will give me some geometry that last this last result. I'm hoping that now you will see some geometry. So let me remind you what's the Casimir operator. The Casimir operator will be to take all the harmonic oscillators to the square, or given this way or this way. And so if we do the corollary twice, so if we take a radiating function, then we apply the Casimir operator, we get a radiating function, and that function has its far field pattern will be the Laplace-Beltrami operator of the function. So in a sense, the Casimir operator has far-field pattern equal to the Laplace-Beltrami operator. I think this is nice for us. Okay. And with that, I finish. Actually, I finished on time. So, what is? Hey. You see, I had an extra slice. Anyways, that's the versions. Oh man, I had a picture of Adolfo there in my exam. Adolfo was my undergraduate thesis advisor, and it has been only a quarter of a century since I finished with him. So, and he, well, I really want to show the picture, and also not to really to say that I thank you to you for. I mean, I think Adolfo gives always. I mean, he was a wise man 25 years ago, and now he's officially a wise man. And he always gives like the right advice, and he gave me a lot in that time. I mean, and I really appreciate, and I really want to be here, and thank you for all the things you do. Thank you. And let me give you a small present. And now I can take a picture with him, because please. Another picture that the one I. Okay. Thank you. Sure. You get the far-field pattern, and then you do that for many directions. And here, the main point is that these guys had the information for the what is the boundary like. They have the information. You can reconstruct from these guys, reconstruct the boundary of the object.